So today we're going to be learning about divisibility rules, prime numbers, greatest common factor, and how they all interrelate. So I'm going to start off with just day one of today's lesson, which is going to focus specifically on divisibility rules, prime numbers, and prime factorization. So for divisibility rules, I'm just going to run through them pretty quickly, and I'm going to use the number 39, that's a 9, 24. And there's the rest of my 2. So 3924, 3,924. So for the first rule, which is the rule for 2, if a number is divisible by 2, it will end in 0, 2, 4, 6, or 8. So because 3924 ends in 4, then this particular number is divisible by 2. So I'm going to put yes here. I'm having trouble with my stylus writing. And then for divisibility rule number 3, to apply this one, we've got to add up the digits of the number. And if it's divisible by 3, that sum, then the entire number is divisible by 3. And the 9's rule is the same exact rule. So I'm going to add up these digits, 3 plus 9 plus 2 plus 4, and I'm going to write that out for both the 3's and the 9's at the same time. And so I've got 3 plus 9 plus 2 and plus 4. And so if you add those together, you've got 3 and 9 is 12, plus 2 is 14, plus 4 is 18. So I'm going to write that out for the 9's as well. And so for the 3's rule, if this sum, which is 18, is divisible by 3, which it is, it would be 6. And then for the 9's rule, if the sum is divisible by 9, which it is because it's 2, then yes, it's 3,924 is divisible by both 3 and 9. Yep, by both 3 and 9. Then we're going to move on to the 4's rule. So a number is divisible by 4 if the last 2 digits are divisible by 4. So if we look at 24, since 24 is divisible by 4, so is 3,924. So my answer for this one would also be yes. For the 5's rule, you just have to know that if the number ends in 0 or 5, then that number is divisible by 5. Since 4 is not 0 or 5, then our answer most definitely is going to be no. For the 6th rule, you've already applied the rule for 2 and 3, and since 2 times 3 is indeed 6, if it's yes to both of these, then it'll be yes for 6. So since our particular number was yes to 2 and yes to 3, that means 6 is also going to divide into 3,924. So we know that 6 divides in there. For 7, this is a crazy rule. Cross off the last digit, which would be to cross off the 4, double it, which means to multiply that 4 that you crossed off by 2, which is 8, and then subtract it. So you would have to take 392, because that's what's left, and subtract 8 from it, all in your head. And then if that new number is divisible by 7, the whole original number is divisible by 7. Well, quite honestly, this is kind of a stupid rule. I don't even follow that rule. By the time you do all that, you might as well just take the number and divide it by 7, either with your calculator or through long division. So I would just put a note on here, just divide by 7. You know, the oddest numbers are divisible by 7. So usually, you know, if you think that a number is prime, which we'll talk about that definition in a minute, 9 times out of 10, really it's the number's divisible by 7, you just didn't try it. And then for the 8's rule, right here, it's also kind of an odd rule because you're going to look at it's similar to the 4's rule because you're going to look at the last 3 digits and see if they're divisible by 8 rather than the last 2. And so here we'd be looking at 924 to see if it's divisible by 8. So if you can do that in your head, great. But 924 for a lot of you is kind of a big number in order to divide by 8. I like to just look at it this way. If it's divisible by 2 and 4, then it's possible the number's divisible by 8. Not 100% certain like our 6 rule was, and the reason is because you can divide 2 into 4. In other words, this number might be just divisible by 4, but it would need another 2 in addition to the 4 in order for 8 to go in there. So oftentimes if you've divided the number by 4, you've actually performed that division. If the quotient, the answer to that division problem, is even, then 8 is going to go in there. So if you've already applied the 4's rule, which generally you have, it is possible 8 will go in there. So generally I like to add the following comment. Instead of this, if 2 and 4 are yes, I'm going to have to get a new stylus the next time. This one's not working out. 8 might, and that's an emphasis on the word might, work, meaning divide in there. And so I'm going to emphasize, I think I'll use a marker. I'm going to emphasize that word might. Might. Not 100% sure. Okay. So then we come to the 10's rule, which you should be familiar with because we already did the 9, remember. If the last digit is 0, then definitely 10 will divide in there. Well, our last digit here is 4, so then our answer is going to be a resounding no. And I just want to point out also that if your last number is 0 and then you have another number here that's also 0, so if you have 0, 0, then whatever power of 10 that you attach a 1 onto that, so with a 0, 0, attach a 1 onto it, that's 100. That means 100 is going to divide into the number. If you have 3 zeros, so 0, 0, 0, attach a 1 into the front of that, 1,000 is going to divide into there. So anytime you have number ending in multiple zeros, that power of 10 is going to divide in there. So good to know. Now number 11. This is also another goofy rule. It does work, but it's so complicated who's actually going to remember that rule. So I don't use this rule. And quite honestly, by the time I hit my divisibility rule for 10, I'm pretty much done, because then after 10 I'm going to apply all of my prime numbers and see if those divide into a number. Or, like for instance, if you look at the rule for 12, so the rule for 12 says if the number is divisible by 3 and 4, well, 3 times 4 is 12, so then 12 is going to go in there. You know, that makes sense. So oftentimes, like if I'm looking at 14, which is not prime, but 2 times 7 is 14, and you've already tested the number for 2 and 7, then you're going to know 14 goes in there. But generally, I only go through the first 10 divisibility rules. So don't worry about the rest. All right, so let's look at prime numbers. So as you look at this sieve of Eratosthenes, Eratosthenes was a Greek mathematician who discovered this sieve, and a sieve is kind of like a colander or a drainer or a strainer, whatever word you use for that contraption that you, once you're done boiling your vegetables on the stove, for instance, in water, and you want to drain all that water out, you pour it into this strainer, and all the water comes out, but what's left in the strainer is your vegetables or whatever it is that you're trying to drain and get rid of that water, that liquid. So our prime numbers are like the vegetables in that strainer, and we're trying to get rid of all the water, which is the non-prime numbers. And once we're done with this, we will look at the definition of a prime number. So instead of following exactly the guidelines that you see written here, here's what I would do. So I'm going to take my pen, and I'm going to have different colors, and if you have different colors, that would be awesome, because that would be helpful. But I'm going to start out by crossing out 1. 1 is not prime. A lot of kids think it's prime, but it's not, and I'll explain when we're looking at prime factorization why 1 is not a prime number. Our first prime number is 2. So we're going to circle 2. It is our smallest prime number and the only even prime number. So we are going to cross out any number out of this 100 that is divisible by 2 because they will not be considered prime. So based upon our divisibility rules, any number that ends in 2, 4, 6, 8, or 0 is divisible by 2. So what's nice is this sieve is arranged in these wonderful columns where all the columns end in the same number. So this entire column here all ends in 2. Here we end in 4, 6, 8, and 10. So all of those numbers are divisible by 2. So I'm just going to cancel out all of these columns because they all have a common factor of 2, and that will make them so that they are no longer prime. And it also got rid of half our numbers, which is awesome. Alright, so then we're going to go to the next number, which is 3. 3 happens to also be prime, so I'm going to circle 3. And I'm going to cross out any number that is divisible by 3. So we're going to have to count by 3s. So when you count by 3s, you are not going to count 3 first. 4 will be your first one, so it's going to go 1, 2, 3. 6 is divisible by 3, but it's already crossed out. So then count 3 more. 1, 2, 3, and we come to 9. So 9 needs to be crossed out. So there's our first factor of 3 that hasn't been crossed out, and then so they'll keep counting by 3s from here on out and cross out. So I'm going to be quiet and count by 3s. And make sure you're looking at the numbers you're crossing out, because although the first few numbers you recognize, oh, 15 is divisible by 3, but then as we go further along up towards 100, you're going to be surprised at what numbers are divisible by 3, because a lot of kids will tell me that certain numbers are prime when in reality if you apply that 3's rule, add up the digits, and if that sum is divisible by 3, so is the number, you might be surprised. So here we go. 21, 27, 33, 39, 45, 51. Now 51 is one of those numbers that lots of kids think is prime because it ends in 1. But if you add 5 plus 1, that sum is 6. And because 6 is divisible by 3, so is the number 51. 57, again, a number that a lot of kids are not sure of, especially if you're not really strong in your multiplication tables, but 5 plus 7 is 12. 12 is divisible by 3. 63, 69, 75, 81, 87, 93, and 99. So then the next number that we come to is 4. It's crossed out, so we're going to skip on to 5. And 5 is indeed prime. And then we're going to cross out any number that is divisible by 5 that hasn't already been crossed out. So by our divisibility rules, we know that if a number ends in 5 or 0, it is divisible by 5. So again, because we have these lovely columns, this whole column ends in 5, and this whole column ends in 0. Well, we've already canceled out the 0, the tens column, if you will. So all we have left to do is cross out anything in the 5s column that hasn't already been crossed out. So anything that ends in 5. The next number we come to is 6, and it's already been crossed out, and so then we come to 7. Well, 7 is prime, so we're going to circle it. And then you're going to count by 7s, and most of the 7s, or the multiples of 7s, have already been crossed out. You should come up with 3 of them. So as you count by 7, again, make sure that you're counting correctly. We're not starting with 7, we're starting with 8 as our first one. So 8 would be 1, 2, 3, 4, 5, 6, 7. 14 makes sense. You should know that's a multiple of 7. 1, 2, 3, 4, 5, 6, 7. 21's already crossed out. And then I'm going to let you keep going from here and count. $49 is the first one that we come to that is a multiple of 7. In other words, it's divisible by 7, but has not been crossed out. So again, as you're counting, make sure you're looking at those numbers, whether they're crossed out or not, and thinking, oh, I didn't realize 7 went in there. So your next one would be 56, but it's already crossed out. 63, it's crossed out. 70, that makes sense. 77, now there's one that's not crossed out. That one shouldn't be surprising. 84, a lot of you wouldn't realize that 84 is divisible by 7. 91 is one of those big, interesting numbers. A lot of you think that's prime. It's actually divisible by 7. And then 98 is also divisible by 7. It's already crossed out. So there are your 3, 49, 77, and 91. Then all the rest that are not crossed out are considered prime. So what I'm going to do is I'm going to highlight those, and I think if I highlight it in yellow, yep, that still shows up. So I'm going to highlight all of my primes in yellow, and I'm going to go down in rows, and I would suggest that if you can, you do the same. So double check yours and make sure that you have all the same numbers that I have. Okay, so all in all, you should have 25. So let me just quickly count. So I showed 25. So there are your 25 primes, and if I were you, I would set up a timetable from which to memorize these. So it seems like, I don't know how I'm going to memorize 25 numbers, but you already know most of the first few. So for instance, whether you realize it or not, these numbers from here to here, we're going to call that day 1. That's hard to see, but that's day 1. So you're going to learn all of the 1s, the 10s, and the 20s. So you should really already know 2, I could point to pop up, 2, 3, 5, 7, 11, 13, 17, 19. Those should be a no-brainer. Those are ones you've been familiar with for years, and as soon as we come up with a definition for prime, which I'll give you here in a second, you'll go, oh yeah, that makes sense, I know that. So really all we're adding here is the 20s, and 20s has 2, 23 and 29. So then I would suggest that for day 3, we're going to add on, let's add on these 2. So this will be day 2. And then for day 3, we're going to add on these 3 rows, let's just say, because these are easy. There's not many in these rows. So this is day 3. And then finally on day 4, you're going to add these last 3. So if you put them on flashcards and study them, it should be a piece of cake. So that's my suggestion. Put these on flashcards and study them. So what's the definition of prime number? So a prime number part of my writing. So that's an N, not an R. So a prime number is a number divisible by 1 and itself. Only. Emphasis on only. Those are the only factors of a prime number, 1 in itself. So as you're looking at the number 2, the only numbers that multiply to give you 2 are 1 and 2. There are no other 2 numbers that multiply to give you 2. 13, the only 2 numbers that multiply to give you 13 are 1 and 13. 43, the only numbers that multiply to give you 43 are 1 and 43. In converse to this, I guess, the opposite of this would be, let's look at the number 64. So where's 64? Right here. So if you look at number 64, it's crossed out because it's not prime. That's because it has more numbers than 1 and 64 that multiply to give it to you. You've got 2 and 32. 3 doesn't go in there. You've got, let's see, 4 goes in there 16 times. And then 5 doesn't go in, so you got 4 and 16. 5 doesn't go in there, 6 doesn't go in there, 7 doesn't go in there, 8 and 8 is 64. So you heard me using my divisibility rules as I was going through those. So numbers that have more factors than just 1 in itself, those actually have a special name as well. And so a composite number that's an O, by the way, is not prime. So I really shortened the definition to that. Basically, a composite number has more factors than just 1 in itself. I will say that 0 is considered neither prime nor composite, so it's the only number that is neither prime nor composite. But other than that, every other number falls into the category of prime or composite. 1 is that kind of fishy number where you're like, well, why can't 1 be prime? It's 1 times 1 is 1. Well, 1 is also an identity. You could have 1/2 times 2 is also 1. I mean, I could go through this all day long. I guess you could do that with other numbers, but I'm going to also show you another argument that people have when we look at prime factorization. So let's go to prime factorization now. So move on to the next page. All right, so let's look at some of these numbers, and we're going to use our divisibility rules, and we're going to prime factor them. So after we look at the first number, I'm going to explain why 1 is not prime. So you can use any numbers that you want to multiply to give you 60, except for 1 and 60. We never want to use 1 as one of our 2 factors. So I'm going to use what's called prime factor trees. I'll show you one other method. You can use that if you want to. I don't particularly care for it, but that's just me. So any 2 numbers that multiply to give you 60. So 2 and 30, 3 and 20, 4 and 15, 5 and 12, 6 and 10. Any of those will work. I'm going to choose 6 and 10. Now, 6 and 10 are not prime. We're going to keep going until we break every number down into its prime number. So, and when you get to a prime number, circle it. So 6 can be broken down into 2 times 3. And based upon what we just did, both 2 and 3 are prime numbers. So we're going to circle those. It's kind of like the fruit at the end of a branch. And you never see branches sticking out of the end of your fruit. So I should never see branches sticking out of a number I've circled. I have not circled 6 because it's not prime. Now 10 is not prime, so I'm going to keep going with 10. So 10, you only have one choice, and that would be 2 and 5. Then there are 2 different ways that you could write out your prime factorization. The first way would be expanded form. So we always write our primes from smallest prime to highest prime using multiplication dots. So expanded form would be 2 times 2 times 3 times 5. Not my favorite. It's useful in certain instances, which you'll see later, but typically, if you're not told otherwise, we like to write it in exponential form. So because we have two 2's, that means I've got 2 to the second power times, I only have one 3, so it's just a 3, and I only have one 5, so it's a 5. So this is my preferred method, unless you're told to put it in expanded form, for prime factorization. Now the reason why 1 is not considered prime is because in every prime factorization should have one unique answer. There shouldn't be multiple answers that students can come up with for the prime factorization of 60. Everybody should come up with 2 squared times 3 times 5. No other variations. So if 1 were considered a prime number, I could have an exponential form that looks like this. 1 times 2 squared, whoops, that's 2 squared, times 3 times 5. So that would make 2 different prime factorizations for 60. I could also have 1 squared times 2 to the second. I guess that one above there doesn't really look like a second, but it is, times 3 times 5. This also has the same value as 60 because 1 squared is 1 times all of this, which is 60. Same thing here. This 1 has no effect on the value of 2 squared times 3 times 5. So both of these give the same value when remultiplied of 60. So because 1 can, and I could do 1 cubed times 2 squared times 3 times 5, and I could go on and on forever. So because 1 can create a non-unique, I'm trying to erase, and for whatever reason I can't erase. Why is it not letting me erase? All right, so I'm going to go backwards and take all of these off. Sorry, it's going to be a slow process. For whatever reason, my eraser is not working. Bear with me. Okay. So, uh-oh. Now it's taking away everything. Clearly my iPad is super slow in the erasing department. Oh, yay. Terrific. Okay. Now we're done. So let me redo part of this that just went away. So here's our expanded form. And here's our exponential form. Okay. So this is our final answer. All right, so then the other way that you could have done this, and I'm going to move on and do the others pretty quickly. Some people like to do repetitive division. It's also known as, I think it's known as the ladder approach. So you always start with the smallest known prime, and you keep dividing it into your number until it doesn't divide anymore. Then you move to the next smaller prime, and so on. So the smallest prime is 2. So since the number ends in 0, we know 2 divides in there. So I'm going to start with 2. I can get the top of my 2 there. So 2 divides into 60 30 times. Since 30 ends in 0, I know that 2 goes in there again. So I'm going to divide it by 2 again. And 2 goes into 30 15 times. Since my number ends in 5, I know that 2 is not going to go in there. So then I move on to my next smaller prime, which is 3. Because 1 plus 5 is 6, and 6 is divisible by 3, so is 15, and of course if you know your times tables, you know that 3 times 5 is 15. And 5 is a prime, so as soon as you reach an answer that's a prime number, you can stop. And so then you can take, and you can either write it in expanded form, because you see it right here. If my pointer will come up, there we go, right there. So there's your expanded form, and then from there you could also have put it into the exponential form. So either way is acceptable. I don't like that way, so you're going to see me using the prime factor trees. So let's look at 84. Again, using our divisibility rules, I could divide 84 by 2. 3 goes in there because 8 plus 4 is 12, and 12 is divisible by 3. 4 also divides in there. 5 doesn't go in there. 6 does because both 2 and 3 did. 7 divides in there. 12 divides, I mean, we could go on and on and on. Most of you are probably going to choose, would be my guess, 4 to divide 4 in there. If you can't divide 4 into 84 in your head, then by all means use that calculator. So 4 goes into 8 twice evenly, and then 4 goes into 4 once. Neither one of those is prime, so keep going. 4 becomes 2 and 2, so circle those because 2's are prime. And then 21 becomes 3 times 7, and circle those because those are prime. And because we're done, we have all circled numbers, we can write it in exponential form. So I've got 2 to the second, because I have 2 2's, times 3 times 7. There's my answer. So for 400, again, I'm going to just use a glaring observation that 400 ends in double zeros. Since it ends in double zeros, it must be divisible by a power of 10, which is 100. So 4 times 100. But you could have used 2, you could have used 8, I mean, on and on. But the first one that I came up with and could see was 4 and 100. And so 4 can be broken down into 2 and 2, and then circle those because those are prime. And 100 can be broken down into 10 times 10. You could have also used, 4 and 25, again, just as long as we all end up with the same answer. And then 10 gets broken into 2 and 5, both of which are prime, and 2 and 5. Again, both are prime. So when you've got a lot of numbers, it might be to your advantage to start crossing them out as you count them. So our smallest prime is 2, so I have 1, 2, 3, 4 2's. So I'm going to write 2 to the 4th. And then our next lowest prime are 5's, and that's all I have left. So I have 1, 2 5's. So I'm going to be multiplying that by 5 to the second. And the nice thing for you to do once you prime factor it is to actually, you can throw this in the calculator and see, does it actually give you the number you started with? Because if this doesn't give you the number you started with over here, then you must have prime factored wrong. And then just double check and make sure that you have all primes. You didn't forget to break anything down. All right, so we're going to move on to the next page. So now we're going to apply the greatest common factor to a group of numbers. So greatest common factor just means that we're going to look at this group of numbers and try to figure out what is the biggest number that I can divide into both of them, or all three of them, or however many numbers are in the group. So oftentimes you can just look at a set of numbers and go, okay, I can look at 24 and 60 and I know that 2 goes into both of those, because I'm using my divisibility rules. I also know that 3 goes into both of those. I can divide 4 into both of those. I can't divide 5 because that's not divisible by 5. 6 goes into both of them, but not 7, not 8, not 9, not 10, not 11, 12. 12 goes into both these, and I can just keep going until I can maybe determine what the biggest number is. Sometimes that's easy for some of you, sometimes not so easy. So here's a method that we can use to figure out the greatest common factor, the biggest number that divides into a group of numbers. So I'm going to use prime factorization. So I'm going to prime factor 24, and you can use whatever numbers you want that multiply to give you 24. 2 and 12, 3 and 8, 4 and 6, doesn't matter. So I'm going to use 4 and 6. Neither 4 or 6 is prime, so keep going. 4 can break down into 2 times 2. Circle those because they're prime. 6 breaks down to 2 times 3. And circle those because those are prime. Then we're going to hold off and wait to put that into exponential form because I'm going to use something different. So then let's look at 60. We prime factored 60 on the previous page. So before I started with 6 and 10, so I'm going to do that again. And then 6 breaks down into 2 and 3. So I'm going to circle each of those. And 10 breaks down into 2 and 5. So I'm going to circle all those primes. So then what we're going to do is we're going to stretch out. I'm going to try to make this a little bit bigger. Let's see if I can make it bigger. Oh, there we go. All right, so I'm going to stretch out my prime. So I'm going to use expanded form for both 24 and 60. So, and I'm going to line up what they have in common. So here's 24. Well, that does not want to erase. So let's try this again. So here's 24. So 24 has 3 2s and a 3. So I'm going to do 2 times 2 times 2 times 3. Then for 60, I'm going to line up all the factors of 60 underneath 24 that they have in common. Now as far as 2 goes, 60 only has 2 2s, 24 has 3 2s. So you can put the 2 2s of 60 anywhere that you want to underneath the 2 2s of 24. I like to put them towards the end. So here's 60's 2 2s. And then 60 also has a 3, so I can line that up with 24's 3. And it has a 5, which doesn't line up with anything under the 24, so you need to give it its own column. So I'm going to draw a line underneath all of it. And then we're going to find the GCF. So GCF equals. You're going to circle what they have in common. They each have a 2 here, and they each have another 2, and they have a 3. What they don't have in common is this 2 here, because there's a blank here. And they don't have this 5 here because there's a blank here. And then you're going to take 1 2 from each of these groups because 24 and 60 have only 2 2s in common. In other words, this has 2 2s that you could take away, and this has 2 2s you could take away. But that's the most, because this one does not have 3 2s to take away or 4 2s to take away because it only has 2. And this only has 2 as far as the most we can take away. I can take away 3 here, but I can't take 3 from this one. So the most 2s that I can take from both of them is 2 each. So in your greatest common factor, you're going to just bring down 1 2 from each of those circled columns, and then we're also bringing down a 3 because they have 1 3 in common, and you're going to multiply those together. 2 times 2 is 4, and 4 times 3 is 12. So you can divide each of these by 12. 24 divided by 12 is 2, and notice that that's what you have left over that's not circled. 60 divided by 12 is 5, and notice that's what you have here that's uncircled. That's what's left over. So then we're going to look at 18 and 27 and go through the same process. So to prime factor 18, I'm going to use, I could use 2 and 8, 3 and 6, either one of those. So I'm going to choose 3 and 6. Circle 3 because it's prime, and then 6 is 2 and 3, and both of those are prime. You only have one choice with 27, and that would be 3 and 9. Circle the 3, and 9 breaks down into 3 and 3. Circle the 3's. So then we're going to stretch them out in expanded form and line up what they have in common. So for 18, and you always want to go from smallest prime to largest prime. So I've got 2 times 3 times 3. For 27, I have 3 3s. So I cannot put one of the 3's here because it does not match up with the 2. So you're going to have to put the first 3 here, the second 3 here, and the third 3 gets its own column. So then we're going to circle what they have in common. They have 1 3 in common and a second 3 in common. So for your GCF, greatest common factor, you're going to bring down a 3 and a second 3, multiply them together, and you get 9. All right, the last, let's see, here we go, hang on, I'm using the wrong thing, so let me move this up. So our last greatest common factor is a group of 3, so it doesn't matter how many things are in your group. You could have 10,000, so long as you look at all the numbers and make sure that they're all divisible by the same thing. So as we look at these, again, if you can't just look at them and say, what's the biggest number I can divide into 16, 24, and 48, start using your prime factor trees. So for 16, I'm choosing to use 4 and 4. You could have used 2 and 8 just as well. And then 4 breaks down into 2 and 2. So circle those. So 16 has 4 2s in it. 24, I'm going to choose to use 4 and 6. Again, that's not your only choice. 4 breaks down into 2 and 2. And 6 breaks down into 2 and 3. And 48, again, we have lots of choices. 4 and 12, 2 and 24. I'm going to go with 6 times 8. 6 breaks down into 2 and 3, both of which are prime. 8, your only choice is 2 and 4. 2 is prime, and 4 breaks down into 2 and 2. So then we're going to stretch them out. So 16 has 4 2s. 24 has 3 2s and a 3. So I'm going to line it up underneath the last of the 3 2s here. And then 3 gets its own column because it has nothing to line up with. 48 has 1, 2, 3, 4 2s and then a 3. So I'm going to line it up here. 1, 2, 3, 4, and then it has a 3. Draw a line. I'm going to move this up a little bit. Okay, so for our GCF, we're going to circle what they have in common. This is the first group of 2s that we can circle because all 3 numbers have to have the prime number in common. So I can't circle this group of 2s because 24 is missing that 2 in common. So all 3 have to have it in common, not just 2. So then the rest would be this group of 2s and this group of 2s. But again, not this group of 3s because the 16 is missing a 3. So therefore, they all do not have a 3 in common, only 2 of them. So then we're going to bring down the 2 from each of those columns that we circled and multiply them together, and we get a GCF of 8. And if you want to check, 16 divided by 8 is 2, and notice that that's what was left uncircled. 24 divided by 8 is 3, that's what was left uncircled. And 48 divided by 8 is 6, and both 2 and 3 were not circled in 48, and 2 times 3 is 6. So 8 is the largest number that we can divide into those groups. Now day 2, we are going to find GCF, but we're going to add variables to it. So stay tuned for day 2.